Pre-Calculus Chapter 6, Lesson 2, we want to look at some more arithmetic with vectors and then how that arithmetic can be applied to problems. And in this lesson we want to look at what we call the dot product of vectors. How do we determine the angle between two vectors, and then the projection of one vector onto another. Now there are a couple ways that we can multiply vectors together. One is called the cross product method, which actually gives us a vector that's perpendicular to the plane of the original two vectors, and that has to deal with vectors in 3 dimensions. We won't cover that in this chapter, but that would be something that we would look at in Chapter 8. The second way that we multiply vectors is what we call the dot product, and that's what we'll be studying in this chapter. Now the interesting thing about a dot product is though you're multiplying one vector times another vector, your answer is not a vector. Your answer actually is simply a number or a scalar. So it's an interesting thing that happens, but that dot product number does represent a couple of things applicationally, which we'll talk about. The dot product, as we said, will give us a scalar number or a single number, and to calculate or to determine the dot product, you simply multiply the a component of one times the a component of the other plus the b component of one times the b component of the other. So if I want to multiply the two vectors 3, 4, and 5, 2 together and arrive at the dot product, I simply multiply the a components, 3 times 5, plus multiply the two b components, 4 times 2, and you'll see that the result is a number. 3 times 5 is 15, plus 2 times 4 is 8, 15 and 8 is 23. So again, the arithmetic of it is not too complicated. We just want to be able to know then, okay, now that I know how to calculate this, how does it apply to different problems? One application of the dot product is that it gives us another way to determine the magnitude of a vector. You remember from previous lessons that to determine the magnitude of a vector, we take the square root of the a component squared plus the b component squared, and we take that square root. So this would be the square root of 16 plus 9, the square root of 25, which is 5. Well, the magnitude of the vector can also be determined by taking the square root of the dot product. So all I have to do is take a vector and multiply it by itself, determine the dot product, and take its square root. So 4 times 4 is 16, plus negative 3 times 3 is 9, so it's 25. If I take the square root of the dot product, it gives me a 5. So that's one very quick application of the dot product. It gives us another way to determine the magnitude of the vector by taking the square root of its dot product. So let's do a couple of examples of determining the dot product. So here, to determine the dot product, I take the a components, which are negative 2, yellow's not going to look very good, let's do this, negative 2 times the negative 5, those are the a components, plus the b components, 7 times negative 8, and add those together. So this is a positive 10 plus a negative, so that's going to be minus 7 times 8 is 56, so this would be a negative 46. And again, you'll notice that we arrive at a single answer, not another vector, a scalar number. The second thing we want to do in this lesson is to be able to determine the angle between two vectors. Now, the angle between two vectors is the angle that would be between them if you were to draw them in their standard position, meaning if both their tails were at the origin. So if this were the origin of a coordinate plane and I drew these two vectors, what would be this angle right here? If I wanted to determine this angle, I would have to imagine this being my origin and then the vector being drawn here and here, and then I could determine the measure of this angle. If I wanted to determine the measure of this angle, then this would be my origin, and then again this would be the two vectors and then the angle in between. So the formula that we're going to give you here in just a moment, which does involve the dot product, is the way to determine the angle between two vectors. But the important thing to remember is that they have to be in standard position, so you have to make some adjustments to the components in order to calculate these two vectors or the angle up in between here. The formula that gives us the angle between them is that the cosine of the angle that's in between is equal to the dot product of the vectors, which is in the numerator, over the two magnitudes multiplied together. So the dot product over the product of the magnitudes gives you the cosine of the angle. So solving for theta, then the inverse function of that would give us the angle. And again, it's important to make sure that the angle is in, or the vectors are in, standard position with the tails at the origin. So for example, what if we wanted to determine the angle between the vector 2, 3 and the vector negative 2, 5? So real quickly, if I was to measure or to quickly sketch these, the vector over 2 up 3 would be this vector here. This would be 2, 3. And then the vector negative 2, 5 would be this vector here. So the question is, what is that angle there? So the dot product of these two vectors over the magnitude of product of the magnitudes of these two vectors will give me that angle. So multiplying the dot product of the two vectors gives me 11. The magnitude of 2, 3 times the magnitude of negative 2, 5, that gives me radical 13 times radical 29. So taking the inverse cosine of those gives me a 55.5 degree angle. So this angle here between those two vectors would be 55.5. Again, the arithmetic isn't too difficult. You just have to remember the formula, remember how to multiply vectors, and then remember how to determine the magnitude. Remember the magnitude being the square root of the A component squared plus the B component squared. A couple of final things before we wrap this video up. Vectors are called orthogonal or perpendicular if the dot product is 0. And that makes sense to us if we take into account this previous formula. If the angle between the two is equal to the dot product over the magnitude, well, you remember the cosine of a 90 degree angle is 0, so that dot product over the magnitudes multiplied together must be 0. The only way for that equation or for that fraction to be 0 is if the numerator has a value of 0. And the only way to have a numerator with a value of 0 would be if you multiplied those two together and got a dot product of 0. So perpendicular vectors will have a dot product of 0. Now, if we were asked to prove that they are orthogonal or perpendicular, we simply multiply them together. If we get a number 0, they're perpendicular. If we get a number other than 0, they're not perpendicular. So if we take the dot product of these two vectors, 2 times 6 is 12. Actually, I wrote this wrong down here. This should be a negative 6 here. So 2 times negative 6 is negative 12, plus 4 times 3, 12. The product is 0, therefore the vectors are orthogonal or perpendicular. Now, how can we tell if they're parallel? Well, the vectors would be parallel if there is a number, some scalar number, that you can multiply by one vector in order to get the other. In other words, our 2 and negative 7, not 2 and negative 7, is the vector 2, negative 7, and the vector negative 4, 14. Are they parallel, orthogonal, or neither? If they're parallel, there should be a number that I can multiply by 2 and by negative 7 to get these two components. If there is such a number that exists, then they are parallel. Or if the dot product is 0, they will be perpendicular. And if neither one of those things can be accomplished, then they are neither. Well, the way to do this is to take one component, 2, and say, okay, what would I multiply that by to get this other component, negative 4, and solve it? Well, 2 times negative 2 gives me negative 4. Now, if these are parallel, if I take this number and multiply it by this and get the other component, then they're parallel. Negative 2 times negative 7 is 14. Therefore, I can take one number, negative 2, a scalar. I can multiply it by this first vector and get the second vector. And because I can do it, then these vectors are parallel.